Hi, everyone. I thought I would record myself solving all 12 of these review problems, since we weren't able to go over all of them in section, and different sections saw different problems. So just to make it complete for everyone, first of all, I encourage you to just try them on your own, of course. There's no sense just sitting here watching me do it if you haven't attempted it yourself first. But feel free to jump around this video. I'll see if I can put like timestamps in the search or the whatever, the time bar, so you can jump to specific problems that you're interested in. As I mentioned, these are fairly difficult. I haven't seen the final exam yet, so the final might end up being similar or might be easier. I don't really know. It doesn't hurt to try some tricky ones. Okay, so this one, we're defining an equivalence relation on the plane, so R2, and we're saying 2 points in the plane are equivalent if their x values are the same. The most important thing you can do for problems like this is draw a picture, honestly. So even before you read the rest of the problem, just think to yourself, okay, we're working in the plane. So here's R2. And we're thinking to ourselves that 2 points are equivalent. So maybe this is x1, y1, this one is x2, y2, that these are equivalent since they have the same x value. Right? So here, x1 equals x2, sort of, you could say they're on the same vertical line. And so yeah, any pair of points on this vertical line will be related to or equivalent to another point on that vertical line. And same idea for any vertical line you take. So when the problem starts talking about equivalence classes, namely right here, it says, okay, R2, we would read this R2 quotiented by the relation tilde, but it doesn't matter how you read it, just this mess of symbols is the set of equivalence classes of this equivalence relation. So it's the set of all equivalence classes where, okay, I'm just defining everything here. So hopefully we remember what an equivalence class is. It's just the set of all points that are equivalent to the thing you're talking about. So for us, an equivalence class is sort of like a vertical line of points. So if you're thinking about the set of all equivalence classes, then what that looks like is, okay, here's an equivalence class, here's an equivalence class, here's an equivalence class. All of these are equivalence classes, right? I could just like pepper the plane with vertical lines. All of these are equivalence classes. And so the claim is the number of equivalence classes, so vertical bars meaning cardinality, the number of equivalence classes is equal to the number of real numbers, which should sort of feel intuitive once I've drawn this picture. Like for every vertical line I'm drawing, there's exactly one real number on the x-axis, I suppose, corresponding to it. And that's actually going to form the basis of our proof. So our proof that these two things have the same cardinality, let me just erase this picture so we have room. Our proof is going to depend heavily on that idea of relating an equivalence class to a point on the x-axis. So you may have thought it up by now, but the idea is to define a function from R to the set of equivalence classes of tilde by saying, you could go in either direction too. I could have gone, from the equivalence classes to the real numbers. Doesn't matter which way you go. Actually, yeah, let's do that. We'll see that direction. So So let's say I give you an equivalence class and I want to spit out a real number. Well, we can define that function by saying, okay, if you give me the equivalence class of a point x comma y, this function should just spit out. Again, pictorially, we're thinking, maybe this is the point xy. This is the equivalence class of xy, all the points equivalent to it. Yeah, you probably just want to spit out where it intersects the x-axis. Right, so literally just spit out x. Okay, so the function ends up being hopefully simpler than what you might expect from this terrible definition or terrible problem statement. And then all that remains is to show that this is a bijection, right? Because if it's a bijection, these two sets have the same cardinality, and then we're done. All right, so 2 steps, injectivity and surjectivity. So I'll just make the claim f is bijective because 1. Here's my proof of injectivity. We'll just say suppose f of, again, we're going to do this thing where we say the function values on 2 different inputs are equal, and then show that the inputs have to be equal. So here I'll just pick the point. Maybe I'll call it xy for this one and x prime, y prime for this one. Call them x1, y1, x2, y2, whatever you prefer. It doesn't really matter. Okay, what does this mean? Well, that exactly means like there's no work to do. This is this, and that's equal to x. So that spits out x. On this side, it's going to spit out x prime. Right, that's what the function does. It takes the x component of the equivalence class and just returns it. So x equals x prime. So that's great. But we're not done, right? We need to also show that y equals y prime. Or actually, yeah, I guess we do need to show that. Let's see. Sorry, yeah, no, that's sufficient. I'm used to proving this backwards, so I'm thinking of the other direction where we are going from R to the set of equivalence classes. But this is actually sufficient, because what does this mean? Well, if x is equal to x prime, then that actually implies these equivalence classes are equal. And the way you can see that is by just recalling what the definition of the equivalence relation was. Right? We said 2 points were equivalent if their x values were equal. We already know our x values are equal, right? That's what we just found down here. X equals x prime. And so, going backwards, that means the ordered pairs were equivalent. So I'll just say the point xy is equivalent to the point x prime y prime. But that means their equivalence classes are equal, right? If your representatives are equivalent, then that's what it means for 2 equivalence classes to be equal. I think it's a little easier if you do go the other direction from here to here, but we showed that in one of the sections, so I'm just doing things a little differently. All right, so injectivity works, surjectivity works as well. Surjectivity, okay, we're thinking our codomain is the real numbers, so I want to start with some real number, call it x. and I want to choose some equivalence class here that maps onto X. There are a bunch of right choices. We know that for any X value I pick, say this is X, there are a ton of equivalence classes that get mapped onto it, right? Anything on the vertical line. So, I mean, you might as well pick y equals 0, but you don't have to. You can pick anything you want. All right, so choose y equals 0 so that f of the equivalence class of this point x comma 0. Well, again, the function is defined to just spit out x. So that's all you need for surjective. We found some equivalence class mapping onto this point we started with. And like I said, the 0 doesn't matter here. You could pick literally any number you want. All right, so that shows there's a bijection between these two sets, which means they have the same cardinality. So I kind of ran out of room, but make sure you write that conclusion at the end of your proof if something like this pops up on the final. All right, let's proceed to number 2. So number 2 is a harder version of number 1. It defines an equivalence relation on R3. You haven't seen much in R3. But really, it's no different. It's just a different equation that we're working with. So instead of saying x1 equals x2, we're saying this weird equation is satisfied. And again, it helps if you have a picture of what this is trying to say. So what I recommend is, okay, think about this and actually think about it. Instead of writing z1, I'll just write z. Think about solving it. Say z equals x squared plus y squared. And if you think back to, I don't know, maybe multivariable calculus, you could think about what kind of surface this is, right? So z equals x squared plus y squared. Well, this is a sort of a paraboloid, I guess you could say. It's like a circular paraboloid. So there's no stretching on either the x or y axes, and it's a nice paraboloidal bowl shape. So you could draw that if you wanted to. There's my parabola in one slice. Here's my parabola in the other slice. I guess I should have drawn that slightly differently. Cool. And maybe I'll make this look nice. All right, there's my paraboloid. I think that's the word for it. I don't know, it's whatever telescope mirrors are ground to look like, so they reflect light in a nice way. I don't know if you guys knew that. Anyway, and what this equivalence relation is saying is sort of 2 points in 3-dimensional space are related if they lie on the same paraboloid, which is a weird thing to say. This is the paraboloid x squared plus y squared, but I mean, I could add some like constant term here and either shift it up or down. Right? So you could have another paraboloid here. It's uglier. There you go. And you could imagine sort of all possible values of C, and you actually partition R3 into a set of sort of infinitely nested cups, I guess you could think of it as. And so that's what we're saying. Okay, we know equivalence relations partition the space you're working in. In this case, the partition is, yeah, it's a set of paraboloids where the only thing that really matters is your z value, how high you're shifting the paraboloid up or down. Okay, so let me erase this. We'll just have that image in our mind. And let's actually work with this thing. Now, phrasing it like that and drawing that picture hopefully makes you think, Okay, for every equivalence class, well, an equivalence class is going to be sort of a paraboloid. And this will be your sort of z value, how high you're shifted on the z-axis. And so there's our bijection. Let's write it down. F, and yeah, maybe this time I will go from R to the set of equivalence classes. Okay, and take a minute to think about what you would define this as. I'm just going to say, notice this time I am starting with R and going this direction. So it's the reverse of what we did last time, just to keep things interesting. So I'm going to say f of, maybe to be as explicit as possible, since we were talking about the z-axis, I'll write z. F of z equals the equivalence class of some point in three-dimensional space. So think about what you might fill in here. We're thinking about a paraboloid, you know, sitting somewhere. Maybe this is the z value you're thinking about. And so, yeah, why not just pick the lowest point of that paraboloid, which is, okay, x equals 0, y equals 0, z equals whatever that lowest point is. When defining these bijections, just do the simplest thing, right? You could pick any other point on the paraboloid, but it's nice to have zeros, so why not? All right, so we need to prove this is a bijection. So again, I'll make that claim and then prove each one. It's injective. Okay, so as always, suppose here I'll say z and z prime have the same function value. Okay, what does that mean? Well, that means, and again, we're going in reverse this time. Well, the function spits out the equivalence class of 0, 0, z. So 0, 0, z. Its equivalence class is equal to the equivalence class of 0, 0, z prime. But again, that means, I mean, if equivalence classes are equal, that means the points themselves are related under that equivalence relation. And then all you have to do is go back and look at what that equivalence relation is. Right, so 2 points are equivalent if this weird equation works. So I'll just write that down in terms of z and z prime. Z squared minus x squared minus y squared. Okay, this is one of the reasons it's nice I picked zeros, equals z prime squared. Apologies for the notation. Prime squared minus, you know, like x prime squared, y prime squared, but those are both 0 as well. Okay, so that implies z squared equals, or sorry, the z's were not supposed to be squared, I just remembered. Pardon that typo. That would kind of ruin things. Okay, so maybe the notation isn't too bad after all. So that straight up implies z equals z prime, which is exactly what you want, right? You start with f of z equals f of z prime, you get z equals z prime, you're injective. That's sort of why I like this direction better, starting with the real number and spitting out the equivalence class. It just feels more natural to me. But both ways work, as we saw in the previous example. To surjective. Okay, this time we want to pick some arbitrary equivalence class. I circled this. Don't be tempted to write 0, 0, z. You should pick an arbitrary equivalence class in here. So I should pick the equivalence class of the point x, y, z. I'm not being thorough enough if I restrict to just 0, 0, z. You have to pick some arbitrary equivalence class. So x, y, z, let it be an equivalence class in the set of equivalence classes. And I want to show there's something mapping onto it. Right? Okay, so say note that our lives would have been much easier if we had picked this one. Right? Zeros are nice to work with. How on earth am I going to get some, some number c spitting out this equivalence class? I don't even know what x, y, and z are. Okay, so it would have been easier if I did pick this. But again, going back to the picture, if we're thinking about some paraboloid, and we're saying all points on a paraboloid are equivalent, it really doesn't matter if I picked, some point XYZ on some weird part of the paraboloid. It's also equivalent to this point down here, which I'll call 0, 0, C maybe. So that's the point we want to work with. And we know XYZ is equivalent to it. So really, we just have to solve for C. We have to figure out what on earth C is. Okay, so take a minute to think about how you might do that. Pause the video if you want to. I'll just go ahead and write it out. Scoot this over here so we can still look at it. All right. So instead of note that, I'll say define C equal to, and this isn't coming totally out of the blue. It kind of looks like the definition of our equivalence relation. And note that this exactly means XYZ is equivalent to the point 0, 0, C. Why? Well, again, just check that this works. Okay, well, Z minus X squared minus Y squared. We want to show, maybe I'll put a question mark, is that actually equal to C minus 0 squared minus 0 squared? Well, yeah, I mean, C is exactly Z minus X squared minus Y squared. The zeros don't matter. So yeah, we're defining it so it works that way. Okay, so that tells us these points are equivalent, right? This one and this one lie on the same paraboloid, the same equivalence class. And so, okay, what point can we pick, right? Remember, we're doing surjectivity. We're trying to find some point, well, we've kind of transitioned. We're trying to find some Z value that maps onto this. Okay, but we've sort of already done it. Right, so f of C, looking back at our definition of f, just spits out the equivalence class of 0, 0, comma, that point. So f of C is the equivalence class of 0, 0, C. But we just said 0, 0, C is equivalent to XYZ. So ta-da, we do get some real number mapping to this equivalence class that we picked at the start. Okay, so that's an exceptionally weird one. I would be surprised if there was an exam problem quite that difficult. That said, if you understand this, you should be able to handle any problem of this sort. Okay. Next up, another geometric flavored one. Let A be the set of points in the plane such that absolute value of x is less than absolute value of y. So again, the important thing here is what does the picture look like? And without a calculator or Desmos or something, you might just try plugging in x and y values and seeing where they fall. But I'll just show you what it looks like to save some time. It actually looks like this shaded sort of hourglass shaped region of the plane. So both of these together are the set A. Cool. So what is the cardinality? This one should come to you almost instantly. Once you draw the picture, you shouldn't have to think about it anymore. The reason being, it's a subset of R2. Okay, so we're thinking subset of R2. Well, R2 has the same cardinality as R. So upper limit, my cardinality is the continuum, right? The cardinality of R. Lower limit, well, check it out. It contains some copy of the real line. In this case, it's the vertical axis, but that's basically still R. It's just in the vertical direction. And so, you could say it contains some copy of R. It's not exactly R, but it's close enough. And therefore, cool, my cardinality is the same as the cardinality of the reals. That should honestly come to you without thinking. If it doesn't, practice these. These are from the section, I think 14.3, which is like comparing cardinalities. Okay, so claim cardinality of A is, call it aleph sub 1 if you want. Let's prove it. Okay, it suffices to show an injection sort of the kind, actually 2 injections. We'll say F going from R to A and G going from A to R2. Okay, sort of exactly the flavor I was working with before, saying, yeah, there's a copy of R contained in A, ta-da, and A is contained in R2, ta-da. And now that we have seen intuition behind injections, we should hopefully think of them that way, as just, them sitting inside a bigger space. All right, so what's our definition going to be? For F, I'm going to say, well, we want to show there's a copy of R sitting inside A. That was the vertical axis. So maybe I'll use Y just to be explicit. I'll say F of Y maps to, well, what point should it map to? Well, like that's your Y value. That's actually the point 0, comma Y. Right. Cool. So let's just write that down. F of Y maps to 0, comma Y. Right, that does start me out in R and spits me out in A. Technically, you should prove, so I'll just say note 0y is actually an A because, well, what's our definition of A? It's the set of points whose x value has absolute value less than or equal to its y value. But I mean, absolute value of 0 is definitely less than or equal to absolute value of whatever y value you pick. Cool. So that's just a sidebar. What do we want to define G as? G says we're taking something in A, so call it x comma y, something within this hourglass shape. And what do we want to spit out? Well, we're allowed to spit out anything in R2. So sometimes the obvious ones are the hardest to think of. It's already in R2. Sort of define the identity function on R2. Just spit out the same point. Totally fine. Okay, then F is injective. And G is injective. First, we'll start with F. So supposing f of y1 equals f of y2, that's the same as saying 0 y1 equals 0 y2. But for 2 points in R2 to be equal, their coordinates have to be equal. Okay, so 0 equals 0, y1 equals y2. Cool, that's all you need for injectivity of F. And G is injective because it's the identity map. You almost don't need to say anything, but let's write it just to be thorough. G of x1, y1 equals G of x2, y2. Well, G is the identity function, so it just spits out x1, y1, x2, y2, says they're equal, ta-da, you're injective. Right? You started with the function values on these points being equal. You showed the points themselves were equal. Like I said, it's almost immediate. You barely need to write anything. So what does this mean? Well, injectivities mean your domain has cardinality less than or equal to your codomain. So for F, our domain was R. Our codomain was A. Sorry, I'm used to doing stuff in functional analysis, having norms and stuff. Okay, cardinality of R is less than or equal to cardinality of A. That's from F. Then G goes from A to R2 injectively, meaning the cardinality of A is less than or equal to the cardinality of R2. But the cardinality of R2 is R. So the cardinality of A is squeezed between the cardinality of A is squeezed between the cardinality of R on both sides. So it has to be equal to that. That's what we wanted to show. Cardinality of the continuum. Awesome. All right, next one. And again, I hope you're pausing the video and jumping around as much as you need to. All right, this one's weird. Here we're thinking of the set of all polynomials, say in the variable x. Technically, you can make polynomials of multiple variables, but we don't want to mess with that. That's hideous. I guess if you like that sort of stuff, you can go into like algebraic geometry or something, which is a really hot field. And we're defining something from P cross P to P. And what that means is your function takes a pair of polynomials, call them P and Q. And I know you're used to seeing this as P of X, Q of X, but we're just saying it's an element of P. So of course it's a polynomial. You could write it as P of X if you want to, but I'm just gonna use a shorthand. Okay, so you take in two polynomials, you spit out their sum. And I just mentioned here, what does sum mean? And of course, the sum of the polynomials evaluated on any x value is just P of X plus Q of X. It's how you sum polynomials every day. Maybe you just don't see it written like this normally. Anyway, the question then is this an injective function? Is this a surjective function? This function f that takes two polynomials and outputs their sum. Okay, again, this one shouldn't be immediate. It should maybe take you 15 seconds. It should be, well, maybe I'm being nice there. It should take you 15 seconds if you're used to thinking of functions like this that take in polynomials and spit out polynomials. Maybe it takes you a few minutes to figure out whether it's injective or surjective. But Once you think of it in the right light, you're thinking, okay, injectivity means distinct pairs. Right, so P1Q1 and P2Q2 should map to distinct sums. And so you think to yourself, okay, if I want to break injectivity and show it's not injective, I would have to find two different pairs of polynomials that when they sum together give me the same polynomial. And phrased like that, it should be actually fairly straightforward. Not 15 seconds, like I suggested, but so we'll say no, and I'll just say let P1 of X maybe be the polynomial. You can pick anything. Let's say X squared plus 2 and Q1 be, I don't know, X minus maybe X cubed minus 3X. You literally pick anything for this first pair. The next idea is to pick your second pair, P2 and Q2, so that they have the same sum. Right? If I add these together, I'll get something. And I want to get the same sum if I were to add P2 and Q2. Okay, so first let's write down what the sum is. So P1 plus Q1 sum together is, let's write it in a nice way, X squared or X cubed plus X squared minus 3X plus 2. And then we'll want to write down the sum for P2 and Q2 as well. Right, we're thinking of sums because that's the function we defined. We want this to also be the exact same polynomial. Right, you can add different polynomials and get the same result. Is basically all we're saying. So how could we do that? Well, I don't know. You could say this is 2x cubed plus x squared plus 3. Again, you can actually pick anything you want for that one. And then you just have to be real careful about what you pick here. So I want like a negative x cubed. That'll ensure when I add those together, I get this term. I already have the x squared, so I don't need an x squared term on Q2. I want a minus 3x, so let's toss that in. And my constant term, oops, my constant term should be plus 2. So I already have a plus 3, that means I need a minus 1 here. Okay, so once I write that down, actually sit down and confirm that I didn't make a mistake. If I add those two together, I get x cubed plus x squared minus 3x plus 2. Yep, cool. So what does this say? Well, that says f of P1, Q1, the sum of P1 and Q1, is equal to the sum of P2 and Q2 but P1, Q1 is not equal to P2, Q2. Right. Obviously, P1 is not equal to P2, Q1 is not equal to Q2. Okay. That's if you do it the hard way. The easy way is just to say, you know, f of, choose any polynomial p. 0 is also a polynomial. And p plus 0 is the same as 0 plus p. But these ordered pairs are technically not the same. They're flipped. So that's an easier way to see it's not injective. But this is something I would maybe expect to see when you're in testing mode and not thinking straight and just going madly and trying weird things. Anyway, so it's not injective. Question number 2, or part B, is it surjective? Again, this should take you not too much thinking. And really, you should sit and think before trying to write anything down. Surjective means I should get out every possible polynomial by adding two polynomials together. And you think for a while and you're like, oh, maybe not. Maybe adding polynomials always makes them like a bigger degree or something. So maybe I'd never get really small polynomials, but you can, like we just saw, the zero polynomial is free. You can add it to anything without changing the polynomial. So I'll say yes. Let p be, little p be an element of the set of all polynomials. Then just f of p comma 0 is p plus 0 is p. So you're surjective. Right? You can always find a pair of polynomials mapping to any polynomial because one of those polynomials can be nothing. Okay, so that one's quicker. So it's not a bijective function because it didn't satisfy both. It wasn't injective, but it is nicely surjective. Number 5, this one's on the weird side as well. I don't think I've ever formally written a function from a power set to a power set of a power set before. But it's defined in a way we have seen before. We've seen this sort of thing where you take, oh, I have a typo here, don't I? Okay, I will have, I'm using the old version here. This is correct in the section notes, but this is the old version. I think the PDF I emailed has this typo. Anyway, this should say X. Put that in red so we know it's a typo. Anyway, you're outputting all subsets of your set X that have cardinality 1. Okay, so since this is a weird function where you take in a subset of the natural numbers and you spit out a set, like a collection of subsets of the natural numbers, it's worth asking some questions about this. So what is the cardinality of the image of 1, 2, 3? Okay, so note F. First of all, what is F of 1, 2, 3? And I guess to be precise here, what should I think about this as? I may have to correct something in this as well. I wrote these problems very quickly without thinking too much about them. Note that, okay, F of 1, 2, 3 should be all subsets of 1, 2, 3 that have cardinality 1. Okay, so what's a subset of 1, 2, 3 with cardinality 1? How about the set containing 1? Or the set containing 2? Or the set containing 3? That's what the image of that looks like. So what's our cardinality here? Well, keep in mind, you're asking about the cardinality of this set, in which there are 3 elements. The elements are sets themselves, because we're working with a power set of a power set, but basically just keep in mind, you know, where the outermost commas are. Right? There are 3 sets separated by commas. So cardinality, I don't think I have to correct anything in how I wrote it. It should be fine. Cardinality of that is 3. Right, a little weirder. What about the pre-image of the set containing 1? That wasn't me stuttering, it's actually a nested set. So the pre-image, let's write out the definition just so we remember it. Call, or I'll just say by definition. preimage of this thing, well, it's the set of all elements in the domain mapping onto it. So what's our domain? Well, our domain is the power set of n. So maybe I'll say it's the set of all x in the power set of n, such that f of x is actually in, how do I want to say this? I guess I'll just be, I'll go straight from the definition and say that's everything that lands in the set we started with, set containing one. Okay, hideous, right? Maybe we can simplify things a bit. If x is an element of the power set, it means it's a subset of n. What is f of x? Well, according to our definition, that's the set of all subsets of x that have cardinality 1. Okay, so I want to say, again, what's the easiest way to write this? Suppose, I guess we could just write that out. It's kind of hideous. All subsets of x so it's getting quite ugly. But for this set to be an element of this set, the set on the right is pretty small, right? There's only one thing in it. So really that means well, the only possible element here, the only thing that's actually an element of the set containing one is the set containing one. It's a mouthful. So this is just, let's see. It's just the set containing one. And then I have to be careful in the sense that I forgot set brackets around here. Okay, because we're thinking about the set of all things that map onto the set containing one. And in this case, yeah, the set of all things with that property. So this in particular, so I'll just write this as an aside, f of this, according to our definition of f, would just be the set containing one. So that's good. That means that's an element of the preimage, but the preimage is the set of all things with that property. So I need an extra pair of set brackets. Anyway, again, that's probably uglier than something you would see on the final. But there you go. Next question, is f injective? And after that is f surjective. So for injectivity, again, we're asking the question, if I start with two distinct elements of my domain, two distinct subsets of the naturals, will they produce distinct things in my codomain? And in this case, you should really think back to part A and think, well, what's happening here is whatever set you give me, it spits out kind of the split version of it. You take all the singleton sets and collect them together. So if I started with a different set, maybe 1, 2, 4, it would spit out the set containing 1, set containing 2, set containing 4, which is distinct from what it spit out in this case. So it should feel injective. But let's prove it. So suppose f of x equals f of y. And what are f of x and f of y? Well, f of x is the set of all subsets of x with cardinality 1, was it? Yeah. And same idea for y, the set of all subsets of y with cardinality 1. Okay, it's useful to write a goal so we can see where we want to get. We want to get to x equals y, but they're sets, right? So that means I want to show x as a subset of y and y as a subset of x. So, okay, let's just do one direction and I'll say the other direction is similar. So x is a subset of y. Why? Well, let x be an x. Then, what do I know? Right, this one's a little tricky to think about. You want to show that if x is in the set x, then it has to be in the set y. All I know is that their images are equal. But what's in their image? Well, the image of the set x is all the singletons. So I might think to myself, I mean, I know at least one singleton containing just x. That'll have to be in the image of x because it has cardinality 1. And f of x is the set of all things with cardinality 1. Okay, and then I know f of x is equal to f of y. So in fact, that has to be an f of y as well. But really, I wanted to show that x was in y. We started with x in capital X. I want to show x in capital Y. How can I do that? Again, pause the video to think if you need to. It comes down to the fact that I guess you could prove it by contradiction. What's the easiest way? No, I think it's easier just to go with the definition of f of y. Again, like thinking back to this example up here, say x was the set containing, or the set containing x was this one that I highlighted, the set containing 2. That actually is because 2 appeared in this set, right? So if we're given some singleton set, x in the image of y, that actually just straight up implies x is in y because it satisfies everything, right? This has cardinality 1. It's an element of this set. Therefore, it has to be, right? X has to be in y. Okay, so that proves that. Then I'll just say y subset of x, similar. So that proves injectivity because we started with f of x equal to f of y and got x equals y. All right, surjective. Again, after some thinking, always think before you write. It'll be on a time limit, but it'll be enough time to sit and think for a while. To be surjective means I need to spit out every possible collection of subsets of n. But again, we think back to this. This only spit out collections of singletons. It's never going to spit out like a collection of sets with 2 elements. So why not say that? So we'll say no, let 1, 2, we'll write it like this. That's an element of my codomain, power set of n. You should actually sit down and think about why that's an element of the power set of n. It's not as straightforward as you might think if you wanted to like prove that. Anyway, it is, take my word for it maybe, and try it on your own. then what I can say is, maybe for the sake of contradiction, suppose there is some element of my domain mapping onto it. So f of x equals this thing. Okay, this immediately gives a contradiction. I mean, because the cardinality of this thing is not equal to 1. Right? We said the function f only spits out subsets of x that have cardinality 1. Here, we're supposing it spits out something with cardinality 2. Not possible. So there you go. It is surjective. So that's that one done. I'll proceed to number 6, which means we're almost halfway done. I'm getting very hungry, so I'm going to try to go quick. We've actually done this one before, part A at least. I didn't phrase it quite exactly like this, but we did all the same legwork. So we're going to start with a set that has 3 elements and a set that has 2 elements, call them A and B. And I'm going to say curly f is the set of all functions from A to B. I intentionally wrote that in a weird way to try and like remind you guys that all functions are relations, and relations are subsets of A cross B, right? They're subsets of whatever sets you started with, rather the Cartesian product of those sets. So f is the set of all functions, R is the set of all relations from A to B. And my question is, what's the cardinality of this set, which is taking all the relations and subtracting those that are functions? First of all, convince yourself that that's actually well defined. It is. And what do we get? Right. First of all, it's nice because you can think about it like this. This is the set of all relations. Functions are much stricter. To be a function, you have to be a relation, but you also have to have the property that for every single input, you output one output. Relations don't have that requirement. So the functions curly f form a subset of the set of all relations. And so R minus f actually works out nicely in this case. R minus f, because one is strictly a subset of one another, or sorry, one is a subset of the other, you can actually split this up. You can't do that in general, right? If they had this relationship where this was R and this was F, and I was looking at R minus F, I would just be looking at this part. So really, I would need to take cardinality of R minus the intersection of the two. But when they're nested, the intersection is actually all of F. So I can just subtract all of it. And what is the cardinality of R? Well, how many relations are there from the set on 3 elements to the set on 2 elements? Again, we've done this. It's how many ways you can fill in this pegboard. There are 6 options. Each one's either going to be filled in or it's not going to be filled in. So it's like 2 to the 6. Right? There's the empty relation. There's the relation where they're all filled in. And then every combination in between of imagining lighting these up. So it's either on or off, so you get a 2. You have 6 options, so you get a 6. Let's keep that actually. If I restricted to functions, then I'm only allowed to output, a single x value or a single y value per x value. So for that, I have 2 options here, 2 options here, 2 options here. So for functions, that's going to be 2 times 2 times 2, which is 2 cubed. So what you get is, what did I say for the first one? 2 to the 6th. And then for functions, it was 2 cubed. So what's that, 64 minus 8, I guess? There are a lot more relations than functions. Right? If we change the question, though, and ask, what if we're not working with finite sets anymore? That was straightforward because we only had 3 elements in one and 2 in the other. What if you're dealing with the entirety of the real numbers? Okay, so I actually ask a simpler question, not what's the cardinality of R minus F, but what's just the cardinality of F. So how many functions are there from the real numbers to the real numbers? The answer may surprise you. Answer is cardinality of F. You probably want to just, I don't know, if I'm thinking back to when I learned this stuff, I would probably jump to just say, oh, it's the cardinality of R. But it's not. It's actually bigger than that. So it's the cardinality of the power set of R. Sometimes you'll see that written instead of aleph 1, call it aleph 2. It's the next biggest infinite cardinal. Why is that? So again, take some time if you need it. Okay, and again, you have to think in terms of like bounding it above and below. So this one's really strange when you see it for the first time, but it's sort of a classical problem. The idea is going to be, so I'll say first, there's a reason I wrote the intro to part A the way I did. Every function is a relation, and in particular, relations can be written as subsets of the Cartesian product of the sets you're working with. In part B, A and B are both the real numbers. So we're saying F is a subset of R2, sort of. So yeah, any function from the real numbers to the real numbers can be thought of as a subset of R2. I mean, you're used to drawing them as, you know, graphs in R2, so maybe that's not super surprising. It's just the collection of ordered pairs that satisfy that, whatever the function definition is. So yeah, it's a subset of R2. Next. Note that. Well, what does this mean? I guess we could say a couple things. The first of which is probably going to seem like it comes out of the blue, but if you're a subset of something, you could also say you're an element of the power set of that thing. We know those two things are equivalent. But we actually know something nice about R cross R, namely, the cardinality of R cross R is equal to the cardinality of R. Right? Okay, so F is an element of the power set of R2. R2 has the same cardinality as R. So what can we do with that? This actually tells you right off the bat that, what are they calling this? Cardinality of F. So yeah, this tells us that the cardinality of F is actually bounded above by cardinality of power set of R. Basically, we're saying R cross and R have the same cardinality. So if you're always an element of that, it works out nicely. I guess you could write an injection if you wanted to, in the sense of, what do we have? If these cardinalities are equal, there's a bijection between them. So there's automatically a bijection between these two sets. I think that was proved in one of your recent homework assignments, that if you have two sets with equal cardinality, their power sets have equal cardinality. So there you go. Being a little hand wavy, but there's our upper bound, right? We were trying to show that it's equal. We at least know that it's less than. So next step, I want to show the inequality in the other direction. So to show f is actually greater than or equal in cardinality to that of the power set of R. You just have one more step, and this also involves something we've seen before. Recall that the cardinality of, I have this pulled up so I can refer back to it. So yeah, the cardinality of the set, I should really give it a name, but of all functions R to 0, 1, that was also a homework problem. Cardinality, or sorry, I already said cardinality. The cardinality of that set was, then all you really need to note is that since F is a subset of this set, or sorry, other way around, since this set is a subset of curly F, right, functions from R to 0, 1 are also functions from R to R. So one's a subset of the other. We get cardinality of the power set of R less than or equal to cardinality of F, which is, you know, just writing this in reverse. So that gets us what we want. Again, probably on the hard side, but fun to see. Let's go on to number 7. Here, this one's also kind of mean because I'm defining a modulus operator on the real numbers, and we've only seen that on the integers so far, saying integers are congruent mod something. You can also do it for real numbers, right? You could say, for example, 3.14 is congruent to 0.14 mod 1. Because their difference is a multiple of 1, or in other words, their difference is an integer. So that's really what mod 1 means when you're talking about congruence of real numbers. It means they have the same fractional part, or the same decimal part, so the same. After the decimal, they're equal, because they differ by an integer. So again, slightly mean to introduce something new like this on a review, but if you can handle this, you can handle anything. So let's see, prove it's an equivalence relation. 1, we need reflexivity. I hate when my eraser activates itself accidentally. So reflexive, we want to show that for all real numbers, X is related to itself, but that's true because, well, X is congruent to X mod 1 in the sense of X minus X equals 0, but that's a multiple of 1, right? It's 0 times 1. So they're congruent mod 1. 2, you want to show symmetry. Again, this one's quick. For symmetry, you want to show that for any pair of real numbers where X is related to Y, you want to get Y related to X. That's true because X related to Y is the same as saying X is congruent to Y mod 1, which is the same as saying their difference is an integer, so multiple of 1, some n and z. But lo and behold, it's the same as saying Y minus X is negative n times 1, which is the same as saying y is congruent to x, which is what we wanted, right? This implies this. Ta-da. Okay, transitive. Transitive, you should just sit and think about for a minute. If two numbers, or I guess if two pairs of real numbers are congruent mod 1, that means they differ by an integer. So go from x to y is a jump by an integer, and then go from y to z, jump by an integer. The question is x to z jumping by an integer? And the answer is yeah, because you're just summing two integers. So for all x, y, z in the reals, what do we get? Suppose x is related to y, and I'll use the and symbol, I suppose. Y is related to z. What does that give us? Well, that's the same as saying x minus y is n, y minus z is m. So that implies x minus z is, you can sort of add those two equations together. So that's n plus m. I didn't write everything explicitly. I should have been like, oh, for some n and m in the integers, and then that's an integer. But I'm really hungry, so that implies that. All right, so it's an equivalence relation. You'll see stuff like this in higher math courses. Becomes a useful equivalence relation, actually. Then we go back and we're doing something similar to questions 1 and 2. What's the cardinality of the set of equivalence classes under this equivalence relation? Well, what you should think is we're dealing with the real number line. And apparently, whatever number I pick, say like 2.2 or something, I automatically know that's equivalent to 1.2, and it's equivalent to 0.2. It's also equivalent to negative 0.8. So I guess the fractional part only really works if you're thinking positively. But anyway, you have that relationship. And so, like, no matter what number you start with, you could start out here, but eventually hop your way back to something between 0 and 1. I guess closed on 0, open on 1. Because 1 is actually equivalent to 0. Right? So you don't need to think about 1 itself, you just think about 0. Anyway, what that means is when you're thinking about the set of equivalence classes, you could create a bijection to this interval, 0, 1. So let's actually do that. Again, pause the video if you want to try for yourself. I'm just going to say define function f. And where do I want to start? My claim is going to be it's the same cardinality as the interval from 0 to 1, half closed, half open. And let's start with, yeah. I'm trying to decide what's easier, starting with the equivalence class or starting with the interval. And I think it's generally easier to start with the interval. Like in previous examples, we started with a real number and mapped to an equivalence class. And that worked out nicely. So let's try this. Yeah, this is fairly quick. So for any x you give me in the interval from 0 to 1, I just spit out the set of all points that are equivalent to x. So spit out equivalence class of x. Ta-da, that's my function. Again, f is bijective because 1 injective suppose f of x equals f of y. Suppose it's good to say they're in our domain from 0 to 1. then that means the equivalence classes are equal. But the question is, are X and Y themselves equal? And the answer is yes. So equivalence classes are equal means their representatives are equivalent. What does that mean? That means X minus Y is a multiple of N for some N and Z. But X and Y were both between 0 and 1. So what does that give you? Well, I suppose it depends on if X is bigger than Y or vice versa. If X is bigger than Y, you're still going to get something between 0 and 1. If Y is bigger than X, it might flip-flop. So, yeah. What does that tell us? Yeah, in either case, it'll be fine. The fact that X minus Y here has to be equal to an integer means that integer is actually going to be forced to be 0. So this implies N equals 0 because X and Y are between 0 and 1. In particular, X minus Y can't be anything other than 0. Right? If X minus Y were 1, that would kind of contradict this. I'll let you guys think about that more. Play around with some numbers, you'll see why it's true. So if X minus Y is 0, that means X equals Y. Surjective holds as well. Why is that? Well, that's because for any equivalence class you pick, how do you find something mapping onto it? Well, you have to be careful because the thing you want to map onto it has to be between 0 and 1. So like, say this was the equivalence class of 3.14. You can't just pick 3.14 to map onto it because it's not between 0 and 1. But you could subtract 3 and get something that's between 0 and 1. And in general, you can always say, if you take that representative and you subtract the integer part of it, or the floor of it, however you want to write it, then that will actually spit out. That'll be in the interval 0 to 1, because you're killing the integer part. And that's going to give you the equivalence class. Don't get confused between floor and equivalence class. I know the symbols look similar, but they're different. The reason that holds is because this is still equivalent to X, right? It's an integer multiple away from X. So it still spits out the same equivalence class. I guess I could say, to be more like precise, it spits out the equivalence class of this. But that, yeah, the integer part doesn't matter. It's equal to that. All right, next one. Prove this by induction. I don't know if any induction proofs are going to be on the final, but I figured I'd include a weird one. So we want it to be true for all n greater than or equal to 2 and all real numbers x that are positive. So let's write our base case down. Of course, we'll start with n equals 2 because that's the lowest number we're claiming this to be true for. And all we have to see is that 1 plus x squared, putting n equals 2 in here. That holds because, maybe I'll just write this out step by step. One plus x squared is 1 plus 2x plus x squared. But that's guaranteed larger than 1 plus 2x. Think about why that is for a second. And then I'll say, you know, this is actually what we wanted. Putting n here, 1 plus 2x, that's 1 plus nx. So why is it true? Well, the only difference is this x squared term, but x is positive, so x squared has to be positive. So I'll just say because x greater than 0 implies x squared greater than 0. So yeah, 1 plus 2x plus something positive is bigger than just 1 plus 2x. Okay, so base case done, inductive step. Inductive step, we always suppose the claim is true for some integer n, and then we want to show it for n plus 1. For all x, right? That's just a given. Then we want to mess around with the quantity 1 plus x to the n plus 1. Okay, but that's just 1 plus x to the n with an extra 1 plus x term multiplied. And okay, my goal is to show that this is bigger than what? So instead of 1 plus 1 or 1 plus nx, my goal is to get to here. Which, I mean, let's work backwards a little. That's the same as 1 plus nx plus x. Right, just distributing that x through. And how could I get there? Well, I'm supposing at least this term is greater than this term. Ooh, so that looks nice, right? And then what about this x? So I guess I could say here, what do I want to do? I think there are a couple ways I could prove this. Yeah. Let's play around with this a little more algebraically before we get there. What if I distributed this, right? So multiply that by 1 and by x. That might look nice. So that would be 1 plus x to the n. So we still have that term from the previous inequality, so that's good. But then we get plus x times that. Okay. And then how am I going to get to my finish line? So let's actually see this through. 1, we know that this first term is bigger than 1 plus n to the x. Okay. That's from that inequality. Then I want to toss a plus x on here. That was my goal. How can I manage that? Well, there's an x here. And think about this term. We know x is positive. So 1 plus x is actually bigger than 1. 1 plus x to an integer power, well, if you start with something bigger than 1 and keep like exponentiating, you're still going to get something bigger than 1. So I'm free to just say, you know, this whole term is bigger than 1. This is x. So all in all, that's actually bigger than x. Right? X times something bigger than 1 is bigger than x. So really, maybe I should have written two inequalities, but you can combine them essentially. This one's bigger than that one's bigger than that one. And that's exactly what we wanted. That's 1 plus, how was I writing this? N plus 1x. Yeah, which proves it inductively. That's what you get by just replacing n's with n plus 1. So, ta-da. In case you had forgotten what induction looks like, and this one's kind of a tricky one, so there you go. All right, now we're on to the bonus problems. These are not going to be stressed heavily on the final exam. They're group theory related and topology related, which is, again, I haven't seen the final. It's either going to be stressed very little or it's going to be like bonus points. So if you want to hang out for these, feel free to. P2 is the set of all polynomials, again, single variable, just so we don't want to mess with other weird stuff, of degree less than or equal to 2. So you get quadratics, you get linear functions, you get constant functions, but you don't get cubics or things like that. Then, similar to how we defined addition in a previous problem, we can define multiplication of polynomials. So the polynomial p times q, well, you just go real number by real number and say p of x times q of x. Again, that's what you're used to doing when you multiply polynomials. It's not actually anything new. Maybe you just haven't seen it written that way. Question, is P2 a group under multiplication? It's worth going through and checking every single property of a group. One, because if it is a group, you'll have to show all of them. Two, it's good practice. If it's not a group, you're only going to need to break one of them. So maybe it won't be necessary to show all of them, but at least it's good practice. So 1, closure. All right, the idea, if I multiply two polynomials together, and each of those polynomials has degree less than or equal to 2, do I get something with degree less than or equal to 2? That's what closure in a group means. You stay inside the group. After thinking for a minute, you should come up with the answer. No. Take p of x equal to x squared, q of x equal to, I don't know, also x squared. Then pq, their multiplication, actually turns out to be x to the 4th, which has degree 4. So it's not an element of the degree 2 or less polynomials. So it's not a group, right? All you needed to check was closure. And that's important because, like I said, if you were just working from the lecture notes, it's easy to miss closure. It's easy just to think, okay, is there an identity? Are there inverses? Is it associative? And actually all of those, do all of those work? Yeah, I think all of them work. And let's verify those. So you might have been tricked if you forgot about closure. So associativity. I'm just going to say this follows from the fact that multiplication of real numbers is associative. Right, generally we wave our hands at associativity because it's annoying. But we know that multiplying two real numbers, it doesn't matter where I put parentheses, p of x and q of x are real numbers. Right? You're evaluating them, they're functions from R to R because they're polynomials. I mean, maybe I should have said that, but it's from R to R. Hopefully that was implicit. So yeah, you get associativity easy enough. Identity, well, we want it to be an identity under multiplication. So given some polynomial p, what can I multiply by p to get itself? Well, just the function 1. Right? Polynomial, maybe I'll call it I of x, I for identity, is actually the identity because p times I of x, and also I times p of x. Again, it's weird to write things this way, I know. Just turns out to be, p of x times I of x, but I of x is 1. Right, so that just saying pi equals ip equals p. If you write it in like group theory notation. 4, how would I find the multiplicative? Oh yeah, maybe inverses fail. I was thinking of addition. So inverses should fail as well. So let's put some X's. Closure. Inverses, at least I think it fails. I haven't worked this out in full detail yet. Let p of x be the polynomial. I want to just say x, right? The identity function. That's an element of P2, certainly. Does it have an inverse? It shouldn't. I'll just say the only way to get P of x times Q of x equal to the identity is if Q of x, it would have to be like 1 over x, right? And even that wouldn't be the identity everywhere because it's not even defined at 0. But this is not in P2. So no inverses under multiplication. There's actually a name for objects like this that, well, aside from it not being closed, if you're closed associative and you have an identity, but maybe you don't have inverses, you're called a monoid. But we're not closed either, so it's not even that. Anyway, not a group. Next one's an awesome one. This is one of the things where, like, okay, you've actually built up enough group theory machinery to prove cool things. And of course, again, it's on the hard side. I'm saying let M2R be a set. And we're going to say it's the set of all 2x2 matrices of real numbers. So you're used to working with 2x2 matrices from linear algebra, hopefully. We don't even have to worry about complex numbers. Just real valued 2x2 matrices. And then define some subset called SL2R. SL stands for special linear. Linear because we're talking about matrices, and matrices represent linear transformations. Special because we're going to have it be the set of everything with unit determinant, which I don't know how much geometry you were taught in linear algebra, but it means that linear transformation doesn't stretch. It may like move things around, it may like rotate and skew things, but the area of whatever object you're working with is going to stay constant. So the special linear matrices are super nice. Anyway, that doesn't really matter. It's just a fun fact. The important thing is just, okay, determinant 1, 2x2 matrices with real numbers. That's the set we're working with. Question, is it a group under matrix multiplication? So again, let's go step by step. First, we want to talk closure. And that's going to be the most important. Actually, I'll leave that for the end. Second, associativity. That follows from the fact that matrix multiplication is associative. Right, so all you're checking is that the group operation is associative, but we know matrix multiplication is associative. It's not commutative. You can't swap matrices, but you can put parentheses wherever you want and do things in whatever order you want. So let's just write follows from associativity of matrix multiplication. Identity. Okay, is there an identity element in SL2R? Well, it would have to be a 2x2 matrix with real entries, and it would have to have determinant 1. And to be an identity element, I mean, by this point, maybe you're thinking it's just the identity matrix, right? Let's try that. I equals the identity matrix. First of all, is it even, sorry, I wrote P2 because I'm thinking of the previous problem. Is it even in SL2R? Yes, it's a 2x2 matrix. It has real valued entries, and well, it has determinant 1, certainly, right? It's like the prototypical example of a matrix with determinant 1. and this is actually the identity of SL2R. I mean, that's why we call it I. Why is that? That's because, you know, A times I equals I times A equals A. I mean, that's true for any matrix, right? The identity matrix commutes. It's one of the few things that commutes with matrices. So I could say it's true for everything in the set of matrices, but in particular, it's true of all the special linear matrices. Inverses is another weird one. So inverses is important. Do we have inverses in the special linear matrix set thing? So here we'll say let A be in SL2R. Then the determinant of A, actually, and let's write it out. It's a 2x2 matrix, so let's call it A, B, C, D, where those are real numbers. So then the determinant we know is AD minus BC equals 1. The inverse, I mean, if you just take the normal matrix inverse, there's a formula for it. I don't know if you remember, but it's 1 over the determinant. And then you multiply it by, okay, you like swap the diagonal entries. You negate the off diagonal entries, at least for a 2x2. Okay, but determinant of A we just said was 1. So really this is just this matrix. And to prove that this inverse, let's call it A inverse actually. To prove that this inverse is in the special linear group, I need to show it has determinant 1. So let's calculate the determinant of A inverse. It's the same as the determinant of D negative B negative C A. But okay, that's dA minus this, right? So that's dA minus negative B times negative C. It's the same as dA minus BC. It's the same as AD minus BC. And it almost seems magical that that pops out. AD minus BC is actually 1. So A inverse is, in fact, in the special linear group. Fun fact, that works for any number of dimensions. It's just harder for higher dimensions. All right, last question, we skipped closure. Is it closed? If I take two matrices in the special linear group and multiply them, do I stay in the special linear group? Do I stay determinant 1 is the question. All right, so let A and B be in SL2R. Then what does that mean? Well, at least these matrices have determinant 1 because I'm given that they're in this set. So what's the determinant of their multiple, A times B? Well, sit and think for a minute. You know a nice property from linear algebra. Namely, the determinant is multiplicative. Determinant of a product of matrices is the product of the determinants. Again, you don't have to know this in Math 8, but I know you've all taken linear algebra, so well, determinant of A is 1, determinant of B is 1. 1 times 1 is 1. That is, it's closed, right? The product actually does land back in the group. So yes, it works out. This is one of the many beautiful examples of a certain collection of matrices that forms a group. What this means is that if you take a matrix with determinant 1, we're saying 2 by 2. So you're thinking of linear transformations on the plane. And yeah, you take any pair of linear transformations on the plane that preserve area, that their composition, right, doing one that preserves area and a second that preserves area, still preserves area. Maybe that feels intuitive. And not only that, but you can undo them. That's what inverses mean, right? So if I have a nice linear transformation of the plane, so I have some like grid here and it squeezes it like that, so it still preserves area. It does some skewing. I can unskew it using a matrix that also has determinant 1. So that's one really nice example. The next two are from topology. So number 11, is this collection a topology? Okay, so remember a topology, the things we write in the set are the things we're declaring to be open. The only open sets are these. And so apparently I'm claiming that the only open sets are the empty set and the sets with infinitely many things in them. Keep in mind, this could mean countable, countably infinite, or uncountable, like the real numbers themselves. Could be either. The answer here, well, again, maybe we'll go step by step. Certainly, the empty set is in there by definition. Right, so this first check, we're just checking that the empty set and the whole space are in there. R is in tau, because the cardinality of R is certainly infinite, it's uncountable, right? So it's like big infinity. So that checks off. Next, you want to check if intersections behave well. And last, you want to check if unions behave well. Let's start with unions. Let A sub alpha be an open set. So, and this is for all alpha in some index set, which I'll call A. What does that mean? I mean, that means either it's an empty set, which I think I'll just ignore that case, or it means the cardinality is infinite. So what about their union? Maybe I shouldn't use A here. Maybe I should use I for index. So the union over however many sets are in this index set of A alpha. Well, I mean, certainly the union is bigger than each of these sets, right? So A alpha is contained in the union. That means the cardinality of A alpha is less than or equal to the cardinality of the union. Right? Unions make things bigger. So that has infinite cardinality, implies this has infinite cardinality. Not writing out all the details, but there you go. So it's fine for unions. Unions of infinite sets are still infinite. If you happen to toss a few empty sets in there, it's not going to change it. So you could write that down as well. How about intersections then? If I take a finite intersection of infinite sets, do I get an infinite set? Think about that for a minute. Maybe you'll come up with the example A equals, you know, the negative numbers and 0. B equals, the positive numbers and 0. But putting them together, their intersection is just 0. It's not infinite cardinality. Okay, so this is an example where the set given is not a topology on the space provided. Because yeah, you can take intersections of infinite sets and get something that's not infinite. I mean, I could have taken like evens and odds and intersected them, or any two sets that are disjoint and intersected them would end up not being, well, I guess that would end up being empty, and empty is an open set, so that doesn't count. But something like this does, right? That has cardinality 1. And then last question, let tau1 and tau2 both be topologies, so they satisfy each of the 3 properties provided. Prove that their intersection is a topology. Okay, so it's weird. You have to recall that a topology is actually a set in its own right. And so you can take intersections of topologies. And what you get, 0 is in their intersection, because, well, tau1 and tau2 are both topologies. So they each individually have the empty set. Similarly, the entire space, X, same logic. Tau1 is a topology, so it has to have the whole space in it. Tau2 is a topology, so it has to have the whole space. So that works out just from definition. Finite intersections, if A and B, I think the professor likes to use like curly O's for open sets. So let's say that. If these are in tau1 intersect tau2, then, well, what does that mean? That means O1 and O2 are in both of the topologies. Maybe I'll say, okay, O1 is in, how do I want to write this? Yeah, O1 and O2 are in the first topology, and O1 and O2 are also open sets in the second topology, because they're both in the intersections. They have to be in each. But tau1 and tau2 are closed under finite intersection, right? They're topologies, so you can take intersections in them and you still stay in the topology. So in particular, O1 intersect O2, those were in tau1, so their intersection has to be in tau1. And O1 intersect O2, they were also in this topology, tau2, so their intersection has to be in tau2. But that implies, right, this thing is in both tau1 and tau2, so it's in the intersection of tau1, tau2. And maybe we'll just say similar for unions, because I need to go eat food. Similar for arbitrary unions, because tau1 and tau2 are already topologies. So if you take a collection of open sets that are in both of them, their union is still an open set in each, and so it's an open set in the intersection. Anyway, that's probably overkill. So that's all. Yeah, if anything's unclear here, feel free to shoot me an email. I'm not going to have any office hours next week. I mean, your midterm is like super early. So yeah, best of luck. Let me know if I can provide any further assistance. Bye.